Okay, we are very happy to have Professor Shou Zhang from Princeton University. He will be talking about the complex number problem and the algorithm. Thank you. Thanks to Rob and thanks to Song bring me back here to give a talk. Last time I gave a talk is about 15 years ago. Probably come here to talk about dynamic systems. So this time I come back to talk about number theory. So I want to talk about some question. It's probably the one of the oldest unsolved question in at least in number theory. I'm not sure in mathematics. So there's a question. We're not completely followed by history past, but I will follow by some question, some challenges. It's first by Fibonacci. Fibonacci is a mathematician in the Middle Age. He's probably not as famous as Archimedes, Newton. Actually, he's a very important person in the history of mathematics, in the sense that he's a middleman between the modern European mathematics and Asian, Middle East, or Persian mathematics. So he's standing exactly in the middle. Because of this reason, he is, of course, very challenged by other people. So one question got a challenge in 1220. So this is a Fibonacci. The question we will challenge is given by a King's scholar, challenge to Fibonacci to find three rational numbers such that their square is an arithmetic progression with common difference is 5. So you want x1 squared minus x2 squared equals 5 equals x2 squared minus 3 squared. So that's the question. So it's a question he faced by scholar of the King's. He's a very smart guy in Pisa, Italy. So now the question why start with a 5? The first one, I guess people challenging probably already know the answer, right? And I will say if I change 5 to some other numbers like 1, 2, 3, that's very, very hard. I will come later. Why 1, 2, 3 cannot really. Probably the question will be too hard for anybody. But if you change 5 to 6, if you want plus 6, this question actually is much easier. The reason is instead of arithmetic progression of squares of rational numbers, we can talk about arithmetic progression of integers. The one obvious arithmetic progression, if in the mind, is 1, 25, and 49. That's perfect arithmetic progression. But if we divide everything by 4, you will end up 7 over 2 squared minus 5 over 2 squared equals 6 over 5 over 2 squared minus 1 over 2 squared. So 6 is not really that hard. Just keep what they're doing. But 7 is not that easy. It should be much harder than this one. In fact, Fibonacci.
What did you say about 1, 2, 3, and 4?
1, 2, 4 is the same thing as 1. That's very hard. I'm going to come later. So after one night, Fibonacci figured out the answer for this question. So that's the answer we find. So the 5, the arithmetic progression you get is 49 over 12 squared, 41 over 12 squared, and 31 over 12 squared. It's a pretty remarkable because if you work in one night, you calculate all the squares of fractions of 2 digits, trying to make up a 5, right? Not only that, he even solved the problem of 7. That's a much harder problem. It's for 63 or 120 squared.
The same night?
Then 37 or 120 squared.
Not possible, we didn't have coffee in Italy yet.
Why should we believe you?
No, you don't need to believe me. Yeah. Okay. So later on, I will tell you the recipe, what kind of a method he used to cook this kind of stuff. Except Fibonacci, I guess he spent the next few days trying to figure out how to do the 1, 2, 3. Then he said he could not do it. Then he made a conjecture, probably one of the very old conjecture by Fibonacci.
Are the solution unique?
What?
Are the solution unique? Other solution?
No, it's not unique.
Not unique.
Yeah, not unique. So once you have one solution, you can use this one, generate infinitely many solutions. So in fact, all the solutions form a group. Yeah, algebra geometry. You already see this is this equation is the intersection of two quadrics. You're a computer genius. Okay, so I give you a hint. Okay, so geometric conjecture. So 1, 2, 3 are not a difference of 3 rational squares. Okay, so I need to give a name for this thing. So this name is called a congruent number. So I give a definition. So this definition is much earlier. For this definition, I will go back to at least 972. It's 1,400 years ago. So the definition is given by Irad. So the question will be the following: given the congruent number problem, so given integer n, find x1, x2, x3, and x2 such that and x1 squared, x2 squared equals n, x2 squared, x3 squared. So such a number is called a congruent number. Congruent, I guess, the meaning is such a number is very special, very harmonic. It's good numbers. It's nothing to do with the congruence we are talking today. So but the meaning something congruence means they're nice.
What was the language?
What?
What was the language in which this term was introduced?
In Persian.
Yes.
Actually, in the manuscript right now, still inside the text in Paris somewhere. So this problem I got from you check the Dixon's 3 volumes of number theory. In volume 2, you can find out where the original problem comes from. And the funny thing is the following. So Fibonacci gave this answer 1, 5, solve this problem 5, 7. In fact, the original problem, the 36 numbers already given, including 5 and 7. So now we are not sure, maybe Fibonacci already read this. I read his manuscript, right? But anyway, he knows so much more than
bridge.
He's rich.
You said he was the bridge between this.
That's right. That's right. So I suspect that probably he knows this thing already. Okay. So the Fibonacci conjecture will took another 400 years to solve. Until Fermat. And the Fermat, because we want to solve this problem, invented the method called infinite descent. After he solved the problem, he proposed Fermat equations. So that's the whole story in the number theory. So the congruent number problem in number theory has a very, very special role. And this problem is still not solved yet. But we have the congruent number problem. This is solved. This is solved by Fermat. 400 years ago. Yeah. But this is not solved yet.
You find all congruent numbers.
But I mean, give the n how to test
Oh, if it's congruent.
is the congruent or not. So it means you really have an algorithm to do that.
Is there a conjectural answer?
Yes, come on, later on. Yeah, so there's many different level of answers. So in fact, there's a conjectural algorithm given by Tano.
By what?
Tano in Rutgers, Professor Rutgers.
Oh,
Yeah. He in 1983, if you assume the Birch and Sondheim conjecture, he gave you algorithm. Yeah, so for any n, you in finding many steps, you can check if the n is congruent or not. But he cannot give you a solution.
I see.
He just said this is congruent. He has no way to give you a solution or not. Okay, so now I try to make a connection to the more common, modern definition of congruent number. The modern definition is written in terms of triangles. So the connection with triangles is given by the following. Divide a triangle. So the theorem, I call the theorem because it's not, I mean, it's a. So n is congruent if and only if n is area of a right. I mean, let's call it the Pythagorean triangle. Pythagorean or triangle means one triangle whose three sides have the rational length. Maybe I just so you have three sides. You have A, B, C, A, B, C. Rational numbers. So area is n. And this one, of course, is also given by two quadratic equations. So n equals 1/2 AB and a squared plus b squared equals c squared. So you have two quadratic equations here. You have two quadratic equations here. So basically say the different same curve in terms of algebraic geometry. But we have to prove it why the different same curve. Okay, so we need to transfer the one equation to other equation. So if you give me by x1 squared,
Just check, right? You
What?
can just check this on a
I'm
computer.
gonna
No,
By hand,
there's
by
an
hand.
algorithm for writing down all Pythagorean.
No, you can't up to a certain point.
No,
Just parameterize.
no, they're parameterized by integers. I mean, you can,
Yeah, but after some signs. if you-
you get three integers and multiply them by a rational number at the end. You take
Oh,
it's a rational curve.
oh, rationals.
Yeah.
Oh, yeah. Oh, yeah, right.
yeah.
Sorry.
Yeah, so you give in the value equation, then come with the right triangle. It's not very hard because you see, this equation tells you can take this term to this side, 2x2 squared, x1 squared plus x3 squared equals 2x2 squared. To get rid of 2, you have to multiply both sides by 2. Once you multiply both sides by 2, the other side will be x1 plus x2, x1 minus x2, no, 3, sorry, x1 minus 3, and this side is 2x2. So that's the right triangle you get. Right? So you see, this relation is really by linear transform. So this theorem is proved by this way. It's not very hard thing, but it's both equations are really beautiful equations. They have a simple translation from one to other. Okay? And as you already noticed that once you transfer this equation to the triangles, you have many tools you can use. One particular tool is that Pythagorean already knows how to write the Pythagorean triangles with three sides are integers. So these probably is really the secret that Fibonacci knows already than other people. So yeah, before I write down the 5, 6, 7, the 3 triangles is 20, 3 of 41 and 6. So that's a 5 you get. And the 6, of course, everybody knows. 3 and 3, 4, 5, 7 slightly complicated. 35 or 12, 24 or 5, 3, 37 or 60.
6 is a perfect number because it's got integer signs.
Yes.
That's a joke, right?
That's right. So now we have a congruent number formula because if you have what's called a primitive Pythagorean, if you require, we try to do something like that. So this equation, s squared plus b squared equals 6 squared. This equation in integers is more or less completely known by Pythagorean. So it's really given by p squared plus q squared. Sorry, p squared minus q squared.
2pq.
2pq and p squared plus q squared.
Both.
Yeah. So that's the equation we know. Because of this reason, then the area is not hard to calculate. So we got the following formula for congruent numbers. So the formula. So there's the n, one integer n is a congruent if and only if n times some number, some square number is the area of that triangle. So the area of this thing is this one times this one divided by 2. But if you write down in the perfect sense, it's a p plus pq, p plus q, p minus q. So that is the
Oh,
formula.
you had 2 2's, you sorted into the R?
What?
There's
What
a
happened to
half in the formula. For
The area.
Oh, divide.
Yeah. So that's the congruent number formula. So in other words, it's not very difficult to write down some congruent numbers. But congruent number problem is that give you n to check if we can find the PQR so that this equation has a solution. This slightly achievement is that you translate the 2 equations become 1 equation. But somehow in algebra geometry already done right away by the different method. So for example, if a Q equals 2, 1, then immediately you get a 6, right? 2, 1, 3. So R equals 1, that's 6. The congruent number problem, we'll have to say maybe you need only concede a square free. If you have square back, it takes away. If a PQ in there 5, 4, then you will get n equals 5. Because if you want to use this thing, the one trick you think about it, if you have many squares on the right hand side, you can forget about square right away. So if you have 5 and 4, 5 plus 4 is a square, 5 minus 4 is a square, 4 itself is a square, right? Don't have anything left. So it's a 5. To make out 7, it's still same thing. You will not going to, because you want many squares. Another possibility of many squares is 16 and 9. Both of them are squares. And the sum is square. Difference is 7. So n equals 7. So probably Fibonacci already knows all these tricks. So then of course he make up this stuff. Then he want to try to use these tricks for n equals 1, it doesn't work. You couldn't get anything. So now we're trying to see to come to the Fermat, so the theorem by Fermat. One, two, three are not congruent. think he proved the theorem somehow right before the Christmas. Then in the Christmas day, he wrote a letter to his friend. He said, I can show one, there's no right triangle whose area is a square. And he was very excited because he discovered a method which he called the most singular method. Because the method only can prove the negative statement, cannot be used to prove the positive statement. Because it's kind of a mathematical induction, but mathematical induction started with something true first. He did the backward. The equivalent to the mathematical induction, but he just doing it in another way. Okay, so let me show how Fermat proved the theorem. So I just take the n equals 1. So assume 1 is a congruent number. Then you have a triangle. So if 1 is congruent, then you have a triangle, particular triangle whose area is a square. Right? You get R square here. You get p plus p square minus q square, 2pq, and p square plus q square. So you want this R, assume 1 is congruent. So you have this triangle, you with this R minimal. So you have a minimal right triangle here. So this R square will be the area PQ, P plus Q, P minus Q. But this minimality is very easy to show that if the product is in the square, everything must be a square. You have no other choice. So by minimality, so everything this term must be a square. So P, Q, all terms in the right hand side are squares. So you have a P equals x squared, Q equals y squared, P plus Q equals u squared, P minus Q equals v squared. So you can show that without minimality this is not true. You can still do something. So in other words, if they have something wrong, then you can check that it's not minimal. So from this picture, you can get another right triangle right away. You get u plus v, u minus v, 2x. So let's check if this is true or not. So you want to check this square plus this square, this square. This square plus this square is twice of u square plus v square. Yeah, twice u square plus v square is 4p. But this one and this thing is 2p. Right? You get a 4p, but p is x squared. 4p is 2x squared. And the area of this thing is this thing times this thing divided by 2. So u squared minus v squared divided by 2. U squared minus v squared is 2q. It's really q, right? So the area is q. That is y squared. Q is one term here. So this R square here. So this right triangle is definitely smaller than this one. So it gets smaller. So this is smaller than this one. Super small if this is something good. Okay, let's give you a contradiction. So that's the Fermat proof. Then you can do something for 2 and 3. Okay, so So that's the ancient story about the convert number problem. But from this equation, somehow you immediately realize that since if we only think about, I mean, here we want everything to be integer. Say I don't care integer because it looks like integer is not really a big deal, right? You can start with the rational number. You can take a PQ, P minus Q, P minus Q, the rational number. If the rational number, then what are you going to do? You can take a P. This side it's a 4 facts. You can take some powers of P out, right? So if we take some powers of Q out, so if this is the equation you start with, so if we divide both sides of star by Q to the 4th power, right? What do you get end up is n times r of Q squared equals P of Q, right? Of third power times P of Q. So that's the equation you get. Right? So in other words, we end up something. So this P of Q, R over Q squared is a solution to an equation ny squared equals x3 minus x. So this is an elliptic curve. So En is an elliptic curve. So if you write, you can draw the real points out without much difficulty. You have the right hand side has 3 zeros. The next 1, 0, and 1 there is basically the picture of this elliptic curve. So the elliptic curve with a node, has a group structure. You have a PQ here. If you have point P, Q.
Not great letters, but
What?
you might want to use different letters.
Different letters, that's right.
Capital A, capital B.
Okay, capital A, capital B, capital C. Then you take this stuff here, get a D here. You have a group structure. You can this has a En has a group structure. Then Q A plus B equals D. In fact, this group structure was discovered. It's not really discovered. But if you know that, it's true. At least it's the first time noticed by Poincaré, because he noticed that this thing has a complex point as a group structure. Then he realized that the rational point as a group structure. And they actually made a conjecture. This group should be finitely generated. So we have a theorem. So En,
Where is n in that elliptic curve?
what?
In that picture, where is the number n?
Number N is just stretch
How much is
your
it?
curve this way and that way.
Okay.
Yeah, so it's all these curves homomorphic to each other. Right. So ENQ is the theorem. And it's a really special case of Mordell conjecture, Mordell theorem. 22 whatever. Q is finally generated. So not only that, in fact, for this very particular elliptic curve,
Abelian group.
yeah, it's abelian group. Abelian probably already noticed by Poincaré. So in fact, for this elliptic curve, not only know the finitely generated, you even know the torsion subgroup. Torsion subgroup means the group elements which has a finite order. This exactly is given by the origin. Origin is the infinite points. Because these two, you see these 2 points only intersect your curve in 2 points. So right, some point is missing. If you take homogenize this equation, then you will see the points in infinity. And this point and these 3 points, because every point here will be double points. So you get x 1 0 0 0 1 0 z multi z square. So any point of that one is not torsion. So now we restate the theorem here. This congruent number formula. We will see very clearly that we want P bigger than Q, right? At least P bigger than Q. P equals Q, we get 0. Not so interesting. I mean, this equation has a trivial solution. P equals Q, R equals 0. Right? That's not counted. So if that is the case, if you exclude this case, so basically we end up the following theorem. Is that n is congruent if and only En of Q is infinite. So that's the basically you change the question. A question for congruent numbers in a model problem about elliptic curves.
I've got n as the area of the triangle.
Yes. Then we, in the 1960s, let's bring to the modern consideration, really the modern world, is called the Burgers-Dye conjecture. Maybe I should. So this conjecture really changes the way of thinking of this question. So far this question is still about geometry, arithmetic. The Burgers-Dye conjecture make you connect to the analytic objects. So it's something called error function. So you have a connection. The error function En of S. So the abstract definition of the En here is given by of En S is given by the product from P 1 minus AP to the negative S to the 1 minus 2S. So this AP is an easier quantity than finding the rational solution. So AP is equal to P plus 1 minus number of solution of the elliptic curve, not over Q, but you want in FP. So FP is a finite field, Z mod PZ. So in other words, instead of consider equation y squared equals, okay,
So the product is over P prime. P is arbitrary positive prime.
let's not divide, say, for example, 2n, for example. Yeah, but it still can define it, 2 and n, but I don't want to be too complicated story. But this equation. So in other words, En of FP is about this solution of xq minus x mod p. What about this equation? I mean the solution of this equation. Well, this one we already have fundamental solutions. You can compute them, then put them together, you get a kind of infinite, you get an Euler product. So if you write this down to that condition, An to the n s power. Not only that, you actually know this series is defined by infinite product. It's convergent about when real part of S is bigger than 3½
Wait, so what is AP? I
What
can't
is-
hear what you said.
AP is defined by this formula.
Oh, there, okay.
And well, this was one of the major object study for the arbitrary elliptic curves. The elliptic curve, we just write down the that's too special. So in fact, we know how to calculate this number precisely. So I can give you the formula for this elliptic curve. By the way, so L is 0 n S equals summation A plus bi. This is 0 I as a Gauss image. You want A plus bi. You count in 1 mod or 1 plus I set of power, so you twice 1 plus I. So just mod this in. So it's infinite A plus bi divided by S squared plus B squared to S power. So probably you don't really need to remember this in. Then you have the Lorentz symbol. I mean that is Jacobi symbol and S squared plus B squared. So this is Jacobi symbol. The Jacobi symbol is a by multiplicative variable. So A and B. If A and B are coprime, then you can write down this as the product. Whatever, if A is a product of primes, B is a product of primes. So this of course is the value plus or minus 1. Where you have is a P and a Q. And the Q, right? The P divided A, Q divided B, whatever. I have powers here. And A, some stuff here. And try to say if A and B squared, well, so this is so the bi multiplicative in A and B. If both of them are prime, that's usually the Lorentz symbol. Right? It is 1 next to 1, you have P, the quadratic residue. Mod Q, and this and otherwise. So this is actually the error function for this elliptic curve. The reason you can calculate this error function because this elliptic curve has much a simpler structure. So you see, this elliptic curve, if I move it, not like it has extra symmetry than usual elliptic curve, because you have ny squared equals x³ minus x. You have extra. I mean, usually elliptic curve don't have many, and then you have x and y goes to x minus y to one symmetry. For this elliptic curve, you can do more. You can get x and y goes to negative x. Then you get negative 1 here because of iy. You have one more symmetry there. So in other words, this elliptic curve has implication by 0 to I. So something called the elliptic curve with a complex implication. This, in fact, is the simplest elliptic curve we know, because it's complex domain. If you want to write on them, exactly given by square. The complex domain is exactly given by this square here, 0, 1. I, so that's a complex domain. The C mod this lattice. You'll see. There's a homomorphic map there. Because of this reason, the error function got calculated by this. Okay, so we got
So it sort of goes back to George's question that when you're just looking over C, you don't see n at all. You can just
No.
stretch these. They're all the same elliptic curve. over
semi-elliptic curve. So that's like the set of same. So even the two elliptic curves of the C is completely the same. Their arithmetic of a Q can be completely different. So in fact, this is I found it rather conjecture. The special case of PSC conjecture is that the order of variation LEM of S. Oh, I forgot to say that. I mean, conjecturally, this kind of related curve, this error function has a holomorphic continuation to whole complex plane. For generally elliptic curve, this is the theorem of Weyers and others. They call the modularity that implies Fermat. Not theorem, but for this particular elliptic curve, this infinite product, you can show this holomorphic property directly by many transform, by a Bose summation formula. It's a much simpler way to do that. So this can be done much earlier than Weyer's work.
That is the order of the pole.
Order of 0.
0.
Yeah, but it's a holomorphic function. It's given by rank of En of Q. So we change the topic completely. Well, so
What made it holomorphic?
what?
What?
Let's
what
get
made
back
it
to series,
holomorphic?
right?
So you get the infinite series. You can write the infinite series as a Manin transform, a certain holomorphic function, certain real valued functions. This function you can use the Bose summation formula to kinetic continuity. So you know this continuity applies from 0 to 1, then probably half to infinity. You can take something equation to switch it. They have a concrete way to do that. But not just for this one. For general elliptic curve, there's no way. So that's why it makes Weyer's work so famous, because you have to use a completely different method.
Well, just for this curve, it's holomorphic, or for every rational curve?
Just for for every rational curve, it's holomorphic. That's the theorem of Weyer's.
It's holomorphic.
Yes,
Oh,
But for
because
this
the
one-
conjecture is based on that assumption. Right?
that's right. But this one was known. This one, the holomorphic property for this one was known very long time ago. Okay, so we change. If we assume this conjecture that n is congruent, if and only if this error function.
So the assertion is that there are no poles. So a priori, you might have poles from.
Yeah, we already know. Okay, so maybe I should write on this end.
That's the previous assumption.
So this already. Okay, maybe write down.
That's a.
It is already. Yeah. And the before I. LEM is holomorphic. Is an entire function. Let's see. So that's like
So for a rational curve, it could have poles.
no.
For elliptic curve,
Uh-huh.
Huh?
It's Wiles' theorem that for any curve over Q, it doesn't have its
Oh.
entire, but in this case, it's much more
Oh, I see.
elementary.
Yeah.
I guess you're saying that this Fermat's last theorem follows from the
From
homomorphicity of all these things.
right.
But the homomorphicity of this one was known long before.
Long before, that's right. That's actually the story that what Shimura told. They say I have this Taniyama Shimura conjecture. They say I don't believe it. Then he go home to do some calculation for elliptical complex multiplication because that's known. Then he translates the modular equation. Modularity is about symmetry of the group. But he noticed you don't need to really check every element of all of these group. You just need to check a few of them. Then become the functional equation. You check a few functional equations. Then they discover a new theorem called the complex theorem. The complex theorem says if you check like a 10 functional equation, then you prove it. Then that's completely misleading for whole industry for many years. But people always try to prove the functional equation first. But before you prove functional equation, it's something hard to prove formula. But they know for CM elliptic curves, they know how to prove all the functional equations. So the first example of modularity is given by Vei. Then Vei popularized this Taniyama Shimura conjecture. It's so popular, It's called Wei conjecture. Forget about Taniyama Shimura. That makes Shimura really angry. Yeah, because the people didn't really believe that until they give the example. Shimura didn't have any example. When they say modular, they don't know anything.
Well, I saw a movie where when Shimura found out about the proof, he said, "I told you so."
Okay, so that's a very nice thing. So so the biconjecture, by the BSD conjecture, and it's congruent if and only if LEN of 1 equals 0. You see, this is some say, well, let's go back home, check the complete this error function, right? To see if it's 0 or not. I mean, you see, this is definitely 0. If the point 0, 0, 1 is not going to work. So somehow you don't really have a method to do that. Okay, so now I give you a couple of things how to calculate this error function. So first thing is a very nice thing is that this error function has a function equation. This has a function equation. So it's given by some number right here, LE and LE epsilon, EN, LEN 2 minus S. This is a take 1 or not take 1. It's 1 is n congruent to 1, 2, 3 mod 8. The next one is n congruent to 5, 7 mod 8. Okay, so if you bring this thing to when s equals 1, you get LEN. I mean, this implies that if you take a Taylor expansion of this series according to s minus 1, that's basically tell you that when n is the consequence is the following: n is an even function of L is an even even function of s minus 1 if n is congruent to 1, 2, 3 mod 8. That's odd if n is congruent to 5, 6, 7 mod 8. So the best will be this one. Well, odd means it must vanish under 1. So one very consequence is that LEN of 1 equals 0 if n is congruent to 5, 6, 7 mod 8. That's very surprising. But what does it mean? If we believe BSD conjecture, every number congruent to 5, 6, 7 mod 8 must be congruent. Right? So that's such a simple statement. So this is the first
We
step.
already settled incongruent to 0 mod 4 from before.
N equals 4.
Congruent, I'm sorry, n, yeah, almost incongruent to 4 mod 8, sorry.
If n is congruent to 4 mod 8, no, I mean the 4, this means the n divided by 4. And when divided by 4, then you can forget about this. You need to only consider the square free numbers.
Ah,
Right? So this wouldn't happen.
square free n's are all we consider.
Yeah.
Otherwise, you just
Otherwise,
otherwise you just take the square root of n, and you just
Ah,
remove the
yeah.
square.
Yeah. So they take care of all the
You get a
cases.
smaller question.
Some trivial argument, okay, fine.
Okay. So the computation of this then is in fact done by Puget. Another very important result of wires is the following. It's an early result, I guess it's 1978. It's like one of the first important result of wires and the codes. They prove the following, that if LEM1 is not 0, then EM of Q is finite. So they really prove one tiny case of BSD conjecture. Right? They cannot prove both sides. It's just say one side is non-vanishing, other side will be zero.
Wait, this is the full Birch-Swinnerton-Dyer conjecture?
For this,
This is the full conjecture?
not full.
Huh?
Even for this case, not full. Full will also tell you the first Taylor expansion, Taylor series. This is a partial weak form. It's just a random part. There are also refinements tell you that what's the Taylor expansion? What's the first, the leading term of this Taylor series look like? That's a complicated thing I don't want to discuss here. But just this conjecture already tell you so much. So Wiles actually, by Wiles result, at least you get some hint there. One result that if n is a congruent, this must be zero. Okay, necessary condition. Right? So I mean, if n is congruent, implies that En1 is 0, of course, by BSD, or this side is by BSD, we don't know yet. Right? And then, I guess it's 9083 channel actually calculate this value. This is LEM for 1 in terms of some equations. We're not going to write on something like ax squared plus by squared plus z squared equals m, this kind of solution. And if you're looking for the equation a, b, c are all positive integers, right? So this has finitely many solutions. Right? So this is, if m is given, you have finitely many solutions because everything is positive, the positive quadratic form. So kind of find a formula for this n in terms of solution for this kind of equation. So in some sense, if you assume BSD, the Tanner's algorithm already solved this 1,000 years old problem, right? Because you calculate this value. But Tanner, for example, at least this thing gives you something called a necessary condition, not sufficient condition, necessary condition. Necessary for n to be a congruent, but not sufficient. So you cannot say even any one of them is congruent or not.
Are there any examples where it is true?
Okay, so now I'm talking about sufficient condition.
Okay. The Fermat is the first case.
Fermat doesn't write any. Oh yeah, no.
What's
Fibonacci is the first case. Fibonacci. Fermat only knows how to prove which one is not congruent. He doesn't know how to prove something is congruent.
Maybe he didn't have enough room.
He did not have enough room to find out.
Okay, so Fermat, we all agree Fermat is the probably most famous non-professional mathematician. A person who figured out how to find a solution is another very famous non-professional mathematician. I'm going to write his work later. So now actually, I'm going to say before I do anything, I write some conjectures. Just based on this.
What is another not?
Another non-professional.
Amateur.
You're attributing what to that other person?
He hasn't written it yet.
I'm not written yet because I just write these two big guy. One knows how to prove there's no solution. One guy knows how to prove there is a solution. So let's try to before I write everything, there's a conjecture due to Goldfield. Goldfield, of course, he never worked on this algebra geometry. He knows he worked on this kind of error series by quadratic twist. So this is conjecture the following. I run the conjecture. Forget about BSD. This is what we know. So let's try to find my formulas. Let's check. So if n is congruent to 5, 6, 7 mod 8, then n is congruent. Right? This is a part of BSD. Second thing is, if n is congruent to 1, 2, 3 mod 8, we can't say it's not congruent. Right? Because you can find an elliptic curve with rank is 2. Right? So this case, but n is not congruent. But we can say if n is congruent to 1, 2, 3 mod 8, then in 100% probability, n is not congruent. So what do I mean that if you count this n from 0 to x is a big interval, you count how many of them are congruent, how many are non-congruent. In 100% the probability is not congruent. So in other words, I mean this is like a very clear, this is like a very clean conjecture there. We know very little about it. Okay, so this is like the conjecture we often refer to BSD conjecture, but it really derived from BSD conjecture. After BSD, then combined with the analytic number theory, like a Goldfield study, all the quadratic twist of error functions.
Do we have any 1, 2, or 3s that are?
Oh, very easy, because I have a congruent number formula.
Huh?
I have a congruent number formula. I have a formula in the blackboard. You take a PQR, you take any P and Q after Y, you can find many,
Oh, okay.
many congruent numbers, which is congruent to 1, 2, 3 mod 8.
Okay.
But those are very few. The conjecture said this is actually very few, very exceptional. So, Dennis asked, I mean, can you give some example which are congruent, not congruent, in general example, not as a very special thing. So there's a theorem, definitely the theorem is the following. So, suppose n is a P is a prime. In this case, we have the two results. One is a Janicki, I don't know how to really use this name. He proved n is 1874. So if P is equal to 3 mod 8, then P is not congruent. Right? Because 1, 2, 3, or 1 is missing. You could not say 1. 1 is a pretty hard case. 1 sometimes congruent, sometimes not congruent. 5 is the next level. Of course, not 2. 2 is only one of them. So this is the result. The second one is somebody I want to pay attention to, called Hingham. 1952. If P is congruent to 5, 7 mod 8, then P is congruent.
Is your non-professional?
Yes. The Hingham is an amazing person. He is he's teaching what they call Germanist, right? School is in German. So when I say not professional,
German literature.
Switzerland.
No, high school.
high school.
Gymnasium.
I mean, maybe between high school and college, advanced high school, right? So it's probably is wrong saying he's not a professional. He's doing something like that.
Weierstrass was a gymnasium.
Yeah, but if you go to the webpage, somehow he's more famous than by his work on the radio engineer. He has many patents there. And he studied math, and he read this book. What do you call this? I forget now. Weber's book, Algebra, the 3 volumes. Somehow he figured out this volume just compute the special values of modular function, all of them. Then he he figured out how to solve this common number problem. And he himself has like 5 papers or whatever. When he was 59, up to the first math paper, he starts with talking about common number problem. Solve this equation. The paper is like 20 pages. Suddenly, the last 5 pages, he jumped to another very famous problem, the Gauss class number 1 problem. Somehow, after a few arguments, said, I also know how to solve the Gauss class number 1 problem. Gauss class number 1 problem is that there's only 9 imaginary quadratic field whose class number is 1. And Gauss knows find 9 of them. Gauss can prove at most 10, but he cannot rule the 1. So that's his conjecture. Then the thing that proved this then get published. So somehow somebody later found there's a mistake inside, there's a gap inside. So I mean, not really recognized by mathematics community until Alan Baker in 1968. And I guess they're stuck. Independently prove that there's no chance imaginary quadratic field plus number is 1. After they prove this thing, I think it's a ego of everybody, such as them, go back to Huygens' paper, find that all Huygens' work is completely correct. And there's some minor mistake inside. And not only that, the Huygens' work is much more elegant than his 2 guys.
But now there are things called Hector points, right?
Now called Huygens theorem. Yeah, Huygens point. Yeah.
There are some Hector points. I don't know
Yes.
if they
Also
are.
the theorem called Huygens theorem. Is like no 10th class number.
Okay, but
So-
what are Hector points?
We're going to talk about it.
Okay.
He used Huygens point and this work. So, but it's so sad because when in 1968, when everybody knows Huygens was correct, he already died 4 years later.
It may not be so sad.
Why?
Just recognition from the outside. I mean,
Outside.
he knew he proved it.
He knew it's proof. Maybe that's right. Yeah. Okay, I hope so. Yeah. But he's an amazing guy because last few years, Yitai Jam proved some big theorem with 58. I say, actually, Huygens proved something with 59. Okay, so that's a Huygens theorem. Huygens theorem proved the theorem definitely not by elementary method, not by I go there and try to find a solution. As Fibonacci doing, he's using the modular functions. As I say, use their Huygens point. So in fact, the couple of non-trivial examples was calculated by Zagier. Zagier knows how to calculate everything. For example, p equals 157. When you mod 8, I think that's 5, right? I'm coming with 5 mod 8. Then Zagier computes this example, and the triangle there it's really big, really big. I don't know how many digits there. I'm not going to write on that. So the x, if you have the triangle A, B, C, so A, I'd rather C there. C is the top. How many digits do you have? There are 48 digits. The bottom you have, that's the main digits there. You have 46 digits. This is the minimal solution for this equation when p is 157. Huygens doesn't really compute it. You can just know there is a solution. I don't know what time right now. I'm almost there. So okay, so just roughly say what Huygens use is in the modern world called complex multiplication. Then he calculated. He use this the evaluation of the modular functions at the same points. In particular, for example, in the modern world x32, this actually is a modular curve. On
This
this
is sort of
curve,
a joke, but how does he know that's reduced
what?
a fraction?
This is probably not very hard, right? 48.
No, that's hard.
It's hard.
Yeah.
I don't know.
If you want to factor it. Oh, you can just check this. No.
Computer GCD.
I mean GCD by Euclidean method.
It's already in the, the coding range. Huh? What?
They're saying you can find Euclidean algorithm.
The Euclidean algorithm probably not very. Yeah, so this is the curve to start with. And on this one, you have these parameters electric curves, E1, E2, phi the kernel of phi isomorphic Z to the NZ, CD2Z. You can find a C1, E1, E2 a CM electric curves. When a CM electric curve, then this will define a point here. And this electric curve is a straight line. Actually, it's isogeny to E. But Hinton didn't know that. Hinton didn't even use this elliptic curve. He used much more complicated one. He used X of H. It's high coverage. This is the hyperbolic curve. This is like elliptic curve. Anyway, he just do all the calculation. He figured out the solution here. And for people who has no experience of CM computation, there's a famous thing. You go to the Google. There's a really nice good story about this number. So if you use a calculator, you find it's almost like integer. It's almost like 6, 4, 0, 3, 20, the third power plus 744 minus 7 to 4 times 10 to the negative 14th power. So you have a very tiny digits there. So that's like the whole thing behind these calculations, this stuff. Okay, so that's all the story. I just write. I forget. I suppose write one theorem myself. So, write one theorem. So I mean, it's a joint work with. I have 2 graduate students and 1 undergraduate student. Ye Tian is in China. Xin Yuan is in Berkeley. I have another undergraduate student, Alex Smith, is in Princeton. He's grew up this year. So we prove that this big conjecture, we suppose, I mean, everything is congruent, everything is 100% congruent. We don't know anything, actually. We don't, I mean, before our theorem, there's no positive proportion. At least right now, we can prove that. So if n congruent to 1, 2, 3 mod 8, then at least 33% are not congruent.
That's about a C, right?
I want to see, that's right. So 2, the congruent to 5, 6, 7, 8. Mod 8 is about 40%. Are congruent. Yeah, so we just basically prove the positive density. So our proof is by proof a weak version. We prove for certain elliptic curve, the BSD is true. So we just prove right on these elliptic curves where we know how to write, where we can check the BSD conjecture, precise formula. So proof by
40%.
40%.
At least.
At least, yeah. Okay, maybe I should have stopped.
What was that date? 974? Remember the date when this problem started?
972.
972.
972, but yeah, but
AD, right?
Is that a congruent number?
congruent number problem was formally stated, written somewhere in the Persian anonymous yeah, you may check it. Go back to check their Dixon's 2 volumes, 2nd volume somewhere about this. Well, there's another famous problem, equally famous, and it's about which integer. It's the sum of 2 cubes. There's also, I mean, there's another equally difficult problem.
Like 1729.
1729, 1729, that's right.
In 2 ways.
In two ways, yeah. There's another problem. This one is interesting because the one elliptic curve we just talked about is a J variant of 1728. This one J variant is 0. There's only 2 elliptic curves. But define all rational numbers with C. So that's actually very. So you see how little we know. The most basic elliptic curve of Russian numbers, we don't know their arithmetic. Yeah, so we are talking about arbitrary elliptic curves. These two elliptic curves are way too more elementary than any other elliptic curves.
Did you say you used only curves through which BSD is known in your work over here?
No, not that many.
No, I said, did you say you used only those curves for which it is known? Exclusively those curves for which it is known in your work? over
Yeah,
here?
in our work, we prove the BSD conjecture for these elliptic curves. Then two sides are equal, then plus, because we have to do some analytic number theory, plus there's some work of the early work of Hisbron. Hisbron assumed BSD conjecture. He proved this in.
Any other questions?
Okay, that's thanks.
So can I just say, if people are interested in dinner, they should stick around and we'll make dinner times.
So that's